for inverse trig functions, if I take the sine, of an angle, and it gives me a number, a ratio, opposite over hypotenuse, right? So if I want to find out what the angle is, that's going to be using the inverse sine function. If I'm given the ratio, and I need to find the angle, that's going to be the inverse function. So, get your unit circle out.
I didn't.
We're going to refer to that lots. Keep it handy. Now you remember on that unit circle that the sine of theta equals what? In general.
One.
Y.
Y.
Sine of theta equals y. All the way around on that unit circle. So, I want to know what theta is when y equals 0.5.
135 degrees.
Not 135.
I thought I did that by accident on my calculator the other day, and I was like, wow, that came in handy.
That was going to be root 2 over 2. 0.5. Look on your circle. Where does 0.5 fall in the y position? What angle is that with?
30.
30 degrees. There's another one. Look in the second quadrant.
330.
300. No, that's it.
330.
Oh my goodness.
Now those are going to be negative.
150. Yeah.
Look in the second quadrant.
150.
150 degrees. Because you got negative root 3 over 2. Now, if we're talking about a function, that causes a problem.
Why?
Because in a function, if I put in one input value, I should get exactly one output value. Whereas with the trig function, the inverse trig function, if I put in 0.5, I can get, just on that unit circle there, I can get two different output values. It could be 30 or 150. Now, I do want to point out, oops, 150 is to here. I wrote, draw my picture wrong. What is the reference angle on 150? 30 degrees.
No.
All of the angles that have the same trig values will have the same reference angles. That's why they are so important. Now, it's really important to keep in mind that that's going to be true for any one of the trig values. So if I want to look at the inverse trig values, I'm going to have to limit the domain of my function in order to accurately represent. Now, any guesses what that's a graph of?
An earthquake.
Alternating size.
Well, actually, you use it for alternating current. That's the sine curve. Have you ever heard of a sine curve
No,
somewhere?
I really thought an earthquake was a good guess.
I said heartbeat.
Okay, heartbeat, well, yeah. Okay, it's the sine curve. Now here, look at this is how it works. If, remember the sine of 0 is 0. Look at your circle graph if you don't believe me. If I go to pi over 2 or 90 degrees, it goes up to 1. You go over to 180 degrees or pi, and it's back down to 0. You go over to 3 pi over 2 or 270, and it's down to negative 1. And you get back to 2 pi, and it's back to 0, and then it just repeats itself.
Is that a coincidence?
No.
Okay.
There's the sine curve shows up in lots and lots and lots and lots of different applications. Okay? Meaning anything that repeats itself can be modeled with like alternating current. Anything with electricity. One we do actually in calculus is modeling the motion of a on a Ferris wheel, the motion of a one seat going all the way around on the Ferris wheel. Goes up, hits a high point, comes down, goes
About
up.
360 degrees.
So it repeats itself. So anything like that you can model with a sine curve. Now, here's what we ran into with our 0.5. This part, you can just listen for this part. I'll tell you when you need to write it down. Okay. 0.5 is right here in my y value. So here's what we ran into. If I want to know the angle that goes with the sine of 0.5, I get a value here and I get a value here. If I continued out this way, I could get values over here too. So here's what we have to do when we look at the inverse function. We are going to limit it to this little part right here. We're going to limit it to this little part right here. Nope. Nope, that's right. Because that covers all the values that sine can have. What's the highest value that sine can have? 1. What's the lowest value that sine can have? -1. Okay? And as it goes around the circle here, you can see that. The highest it ever gets in 1. And if you think about what sine is, it should make sense. Sine is opposite over hypotenuse. Well, the opposite is a leg. You know that the hypotenuse is always longer than a leg in the right triangle. So the little number's always on the top. So it's always between 1 and -1. Okay. When we find an inverse sine, it's going to be either in quadrant 1 or quadrant 4. Like I said, I'm going to give you a short version of this in just a minute. Now, the cosine is a little bit different. So we're going to look at the cosine curve. This is the cosine curve. Now, it looks almost the same. What's different?
It's red.
Where does it start at 0? It starts at 1. The sine started down here at 0, right? It just starts at a different place, and then the shape is exactly the same. If you look at your x values, the x is 1 at 0. It goes down to 0 at pi over 2. Goes down to -1. Goes back up to 0. And winds up at 1 again. Now, the thing is when I do an inverse function for the cosine, if I pick 0.5, I get different values in different places than I did with the sine curve. So when I limit my range, it's going to be right here. In other words, it's going to be not in the first and fourth quadrants. It's going to be in the first and second quadrants.
So sine is first and second.
Sine is first and fourth. Cosine is first and second. Okay, and I'm going to give you a picture of all this when we get done with this. Now the next one is kind of a wild function. That's the tangent function. Okay. It's kind of scary looking. It doesn't have a top or a bottom. It can get as big or as little as you want.
What do they use that in?
Earthquakes.
The place that I see tangent used most often is things like finding the heights of buildings and that sort of thing. They use it in surveying an awful lot. Okay. Look at here. At pi over 2 and -pi over 2, there's a big hole in the function. How come?
Because it started missing. You tell me.
Wait, what?
There's a hole. There's no value for the function at -pi over 2. And there's no value for...
What's that word called? Where death and touch the line.
No, it's not an asymptote.
Oh my god. I thought I was smart.
But, well, actually,
Okay,
so you're right. It would be a vertical asymptote when it gets high. That's good.
Okay. That's
But look at the values at pi over 2.
I'm looking at
The x is, listen, the x is 0, the y is 1. Tangent is y over x. 1 over 0 is undefined.
No.
So, that's why the tangent function is not defined at 0, or at pi over 2, and it's not defined at -pi over 2. It's also not defined at 3 pi over 2. That's why there's those holes in it periodically. So, in order to get a good representation representation of my tangent, I'm going to go from negative pi over 2 to pi over 2, which will be in, again, just like the sine, the first and fourth quadrants.
So would like negative 3 pi over 2, would that be like a coterminal angle or whatever, terminal angle?
Yes, yes, we're going to use that coterminal angle stuff a lot today. Okay, so now here's the part you need to write down. This is what you need to remember for your notes.
There when it goes down.
Okay, so we have to restrict our domain to get a unique answer. So for the sine, the inverse sine of x equals theta. Let me write that correctly. The inverse sine of x equals theta. My theta must be in either the first or second quadrant, and we use the negative values. So we go from negative pi over 2 to pi over 2. Or in degrees, between negative 90 degrees and positive 90 degrees. Inverse cosine. Okay? Now, with the sine ones, something to keep in mind, Douglas took note of it already, is that we're going from negative pi over 2, well that's going to be right here on your little circle, it says 3 pi over 2, so you're going to use some coterminal angle stuff today. Okay, so this angle right here is negative pi over 2 as well as 3 pi over 2. But for the inverse function, this is the one we're going to use. Okay, the cosine, the inverse cosine of x equals theta, its range is going to be in quadrant 1 or quadrant 2. Now I want you to notice if cosine is in quadrant 1, then it's positive. If it's in quadrant 2, the x values are negative, so it's negative. So you can, depending on whether cosine is positive or negative, you can tell, is it in quadrant 1 or quadrant 2? The sine, if it's in quadrant 1, is positive. If it's in quadrant 4, then that's when it's negative. So the cosine is going to be between 0 and pi, or between 0 and 180 degrees. What, Freddie?
Is that theta pi?
That's 0 is less than or equal to theta is less than or equal to pi.
There you go.
Okay, the third function, we're not going to do all the reciprocals, we're just going to do 3. The third inverse function we're going to look at is the inverse tangent of x equals theta. And it's like the sine. When it's in the first quadrant, it's positive. When it's in the fourth quadrant, it's negative. So we have negative pi over 2 is less than or equal to theta, is less than or equal to pi over 2. Negative 90 degrees is less than or equal to theta, is less than or equal to 90 degrees.
Same as sine.
So it's the same as sine. So sine and tangent are the same for the values you get back. So take your calculator. You're going to have troubles today. So the second sine, 0.5. 30 degrees. Now, say second sine, negative 0.5.
Negative 30.
Gives you negative 30. Okay, so now there are other angles that have that degree, but when you do the inverse sine, that's what you're going to get. Okay? So let's evaluate. See if I can keep those up there where I can see them. Not quite. Let's evaluate a couple of these inverse functions. This is using your unit circle. So I want to find the inverse cosine of root 3 over 2. Okay, so get your, it's positive.
So 30.
So 30. When x is root 3 over 2 in the first quadrant, that's 30 degrees.
And that's it.
Wait, how's it 30 degrees?
Hey, look at your unit circle.
You have to look for the x.
Look at the x value and you go ahead and show it, Freddie.
Okay,
You got it?
See this now.
Okay. It says both radians and degrees. So the other correct answer is pi over 3. Now just keep, no, you're right. It's pi over 6.
Yeah.
Thanks for keeping me honest here. Now, keep in mind that if you get something in the fourth quadrant, you're going to need to figure it as a negative angle. Not the one on your circle, but the negative angle. So you'll be looking at like the reference angle.
What?
Okay? How about this one? The inverse sine of 2.
Really don't.
Inverse sine of 2.
So that's
Down,
two
anyway.
I don't know.
Is there any place that the y value is 2 on your
No.
unit circle?
No.
It's 2 times around.
Aaron,
Dang
let me
it.
find. Does not ever happen.
Wait, so sines in the y?
So sine has to be sines in the y, cosines in the x.
Yeah.
Okay, let's look at a couple other ones here. With your unit circle, keep it handy. Let's do the inverse tangent of the square root of 3. Now this is a little bit trickier because, well, let's do the inverse, let's do a negative one so we can play with that a little bit. The inverse tangent of negative root 3. Now this is a little trickier because the tangent is actually a ratio. So what you have to do is look at the ratio of y over x and say when is that ratio going to be equal to the square root of 3. Now first you know it's going to be in the fourth quadrant because it's negative.
315 or the 330. 330.
So at 330 degrees,
Yeah.
if I take y over x, I'm going to get the square root of 3. Okay. Does everybody see that? What's your y value there? Let's just double check. Just so everybody's on the same page.
Negative 1/2.
Negative 1/2. And what's your x value?
Root 3 over 2.
Root 3 over 2. Okay, so I simplify that, and I get negative 1/2 times 2 over root 3. So that's a negative 1 over root 3.
Okay, 300.
So let's go to 300. Let's try that. So y over x. Okay, so the y value at 300 degrees is,
Negative, yeah, that's negative.
or root 3 over 2.
Negative.
And that one's, the y value is negative, right? And the x value is 1/2. Okay, so that's going to be a negative root 3 over 2 times 2 over 1. Negative root 3.
Okay.
Okay, so we know it's at 300 degrees, but that's not in our range. So we're looking at this right here, 300 degrees, right?
So you say negative 6.
Yes. So my reference angle is 60 degrees there, so it's going to be negative 60 degrees or negative pi over 3. Okay?
Can you go back up? Wait, we're finding the reference angle? I mean, I might just get
You have to find the negative angle. So if you need to find one that's coterminal, so it's going to use the same value as the reference angle, but it's going to be
Yeah,
negative.
really good case study.
Oh, okay.
Okay? So that gets you started on those. Now, I got another one for you. This is where you get to use your calculator.
Okay.
I can't know how the calculator tree again. Oh, someone else needs one too?
Yes. Make sure I get them. You guys need to bring those.
Thank you. Mine here is dead.
Okay. So if it's not one of those nice functions that's going to fall in on your those special angles, then you're gonna use your calculator. So to do that, if I have the sine of theta is negative 5/8, you're gonna say the inverse sine of theta is negative 5/8. So put that in your calculator. Get two so I make sure. Second sine, negative 5 divided by 8. Should get a negative 38.7 degrees. Okay. So if all you're finding is just the inverse function, you're done. So now there's two types of problems. The first ones you come to are going to be just like this. And all you have to do is just find whatever your calculator gives you, write it down. And by the way, it's going to ask for radians and degrees in that part. You can do just the degrees today. Okay.
Just do the degrees, right? On what numbers?
Oh,
12
all
through
right.
26.
Yeah, it's written. Okay. Now, if there's a second part to the problem, and it says I want that angle when it's in between 180 and 270, what quadrant is that in?
The third.
Third.
That's right.
That's the third quadrant. So that means this is my reference angle right here. Or I'm going to use it to find my reference angle. So I've got negative 38.7 degrees, but to put that into the
Just
third
add it.
quadrant, I'm going to say 180 degrees plus 38.7 degrees equals 218.7 degrees. So you might have to find a reference angle and then put it into a different quadrant. Okay?
Yep.
We'll do the last one.
Yeah.
So, drawing pictures in the last section is going to be very helpful. If we moved our first one, it would have been here, so then I see, okay, what has the same reference angle in the right quadrant, and you go from there. Okay?
Still recording.
So, we're done.
Oh
You know
my
what?
gosh, you're